You know, we rarely think about the absolute miracle that is breathing, but deep inside you, your blood is solving an impossible puzzle second by second with every single breath. Let's get into it.
So here's the deal. To get oxygen from your lungs, your blood needs to be incredibly sticky, like super glue. But then, a heartbeat later, when it reaches a muscle that's working hard, it has to do a complete 180 and become the opposite, super generous, letting that oxygen go easily. So how in the world can it be a greedy hoarder one moment and a selfless giver the next?
And just look at these two extremes. On the left, you've got the placenta. A fetus has to literally wrestle every last molecule of oxygen away from its mother's blood. That's a loading challenge. Then on the right, you have a muscle that's screaming for fuel. That's an unloading challenge. These are two completely opposite demands, and yet they're handled by the very same system.
And this gets to the heart of what's called the oxygen delivery trade-off. See, if you make the system better at one thing, say loading oxygen, you almost always make it worse at the other. It's a physiological balancing act. So how did life figure this out?
Well, the secret lies in one truly amazing molecule, and its brilliant, elegant playbook for moving oxygen around. We're talking about hemoglobin. And its strategy, well, it's anything but a straight line. All right, here it is, the star of our show, hemoglobin. The easiest way to think about it is like a molecular taxi that has 4 empty seats. Each of those little subunits has an iron atom right in the middle, and that's exactly where our passenger, oxygen, hops on for the ride. And get this, there are about 300 million of these taxis in every single one of your red blood cells.
Now here's where the real magic happens. It's something called cooperative binding. When that first oxygen molecule binds to one of the seats, it actually changes the entire shape of the hemoglobin molecule. This makes it way easier for the second one to bind, and the second one makes it even easier for the third, and so on. It's like the first person getting in the taxi makes the other doors magically fly open. And the result is insane. A 500-fold increase in stickiness from the first oxygen that binds to the last.
And that brilliant trick of cooperativity gives us this famous S-shaped curve. Now, this isn't just a boring graph. This is the entire strategy right here. See that flat part at the top? That's the lungs, where there's tons of oxygen. Hemoglobin loads up almost completely, and it stays loaded, even if oxygen levels dip a little. But now, look at that super steep part. That's what happens in your tissues, where oxygen is lower. A tiny drop in oxygen causes a massive amount of it to be dumped off. It is perfectly designed for both jobs.
But wait, it gets even smarter. The system can actually change the rules of the game in real time depending on what's happening locally. This brings us to something called the Bohr effect, and it's all about letting go of oxygen exactly when and where it's needed most. So what you're seeing here is the curve getting pushed to the right. All a right shift really means is that hemoglobin has a lower affinity for oxygen. It becomes less sticky. And what causes this shift? Well, it's the exact conditions you'd find in a muscle that's going all out.
Think about it. When you're exercising, that muscle is cranking out carbon dioxide and lactic acid, right? That makes the whole area more acidic, and it gets hotter. These things are basically chemical signals that scream at hemoglobin, hey, we are desperate for oxygen over here. And that forces hemoglobin to dump its cargo more easily. It's a beautifully responsive, on-demand delivery system.
And the chemistry behind it is actually pretty simple. The CO2 waste from your tissues pops into a red blood cell. In there, an enzyme helps turn it into carbonic acid. That acid then releases hydrogen ions, and these hydrogen ions, they're the key. They physically bind to hemoglobin and basically kick the oxygen out of its seat. So the more CO2 you make, the more acid you make, and the more oxygen gets delivered. Simple as that. Okay, so that's how we deliver the goods. But what about taking out the trash? The system has to be just as good at getting rid of all that CO2 waste. And this is where the other side of this amazing coin comes into play, the Haldane effect.
The Bohr and Haldane effects are like a perfect tag team. The Bohr effect says that high levels of CO2 help kick oxygen off of hemoglobin. The Haldane effect says that once that oxygen is gone, that very same hemoglobin molecule is now way better at picking up CO2 to take it back to the lungs. They work in perfect harmony. And this slide just shows it perfectly. That top curve is deoxygenated blood, the blood that's just dropped off its oxygen. Look how much more CO2 it can carry. The very act of unloading oxygen turns hemoglobin into a better garbage truck for carbon dioxide. It is an unbelievably efficient 2-for-1 deal. So, yeah, the system works great under normal circumstances. But what happens when things get really extreme? What happens when that trade-off between loading and unloading becomes a genuine matter of life and death?
This is the ultimate physiological test, right? When oxygen is just plain hard to find, like on top of a mountain, or for a fetus inside the womb, what do you prioritize? Should hemoglobin become even stickier to grab every last bit of oxygen it can find, or should it become less sticky to make sure the tissues get whatever little oxygen is on board?
Well, life gives us a really clear answer, and it starts before we're even born. Fetal hemoglobin is actually a different version from what adults have. Its curve is shifted to the left, which just means it has a much higher affinity for oxygen. It's stickier. This is what allows the fetus to literally steal oxygen right out of the mother's blood in the placenta. The priority is obvious: loading.
And evolution completely doubles down on this strategy at high altitude. I mean, look at the bar-headed goose that flies over the Himalayas, or llamas living high up in the Andes. We see the exact same adaptation over and over. They've evolved forms of hemoglobin with a higher oxygen affinity. When the air is thin, the single most important job is just getting oxygen into the blood to begin with.
But what about us? About humans? Well, an amazing natural experiment gave us the answer. Researchers found and studied a family with a rare genetic variant that gives them naturally high-affinity hemoglobin, just like those high-altitude animals.
The results were just striking. When they went to high altitude, the family members with that sticky hemoglobin kept their blood oxygen levels higher. And this is the kicker: their physical performance didn't really drop. They did way better than their own relatives with normal hemoglobin. So the verdict from fetuses, from evolution, and from human genetics is all the same. When oxygen is scarce, you have to prioritize loading. It's the winning strategy.
But, and this is a really important but, there's a dark side to this. A left shift having hemoglobin that's too sticky isn't always a good thing. In the wrong situation, it can be absolutely fatal.
And this is exactly what happens with carbon monoxide poisoning. First, CO latches on the hemoglobin about 250 times stronger than oxygen does. This creates a massive pathological left shift. It locks any remaining oxygen onto hemoglobin so tightly that it can't be released to your tissues. So your blood might be full of oxygen, but your cells are suffocating. And second, by taking up seats in the taxi, CO just reduces how much oxygen your blood can carry in the first place. It is a truly deadly 1-2 punch.
So, when you step back and look at the whole thing, what you see is this just exquisitely balanced system. It uses cooperative binding to solve that fundamental trade-off. It uses local chemical signals to fine-tune delivery on the fly, and it uses evolutionary tweaks to survive in the most extreme places on Earth.
And this really brings us to a final, pretty profound idea. All these physiological principles are incredible. They show us the constraints, the tensions, all the possible solutions to a problem like oxygen delivery. But they can't, on their own, tell us which solution biology will actually choose. For that answer, you have to look at life itself, at evolution, at a developing fetus, at an animal on top of a mountain, to see the breathtakingly elegant solution that biology actually came up with.